Last time we talked about the entropy, how to calculate the entropy if we have, let's say, any gas or any fluid undergo process from 1 to 2, how to calculate the change of entropy delta S, which is equal to integration from 1 to 2 delta Q over T, plus the part actually any actual process should be actually irreversible, and we should have some irreversibilities, and we should have some entropy generation in this case. And we have defined the entropy change for any process to equal to integration from 1 to 2 delta Q over T plus entropy generation. Let's learn today how we can calculate the change of entropy for some substance, starting first of all with the most or the common case when we have a pure substance, like when we have a steam or refrigerant, how to calculate delta S. We have learned in chapter 4, if you remember, we have learned how to calculate delta H. Considering different fluid, considering steam or refrigerant, we can use the table. And also in case of ideal gas, we have learned we have constant specific heat analysis, variable specific heat analysis to calculate delta U and delta H in this case. And we have learned also how to calculate delta U and delta H in case of incompressible substance. In case when we have liquid or solid substance, how we can calculate delta U and delta H as well. Inshallah, today we'll be starting to learn how to calculate delta S. The same, we'll be repeating actually the same procedure, how to calculate delta S for any substance undergo a process. Starting first of all actually with the case when we have when we have a pure substance, like when we have a refrigerant, we have the refrigeration table, or when we have steam, we have also steam table. And this case, actually, in this case, it is very simple and straightforward to calculate delta S in this case, as the value is tabulated in the table directly. So if we have two independent and intensive properties, then in this case, I would be just going to the table. And then actually I can calculate the entropy at case 1 or case 2. So let's say the entropy, how to calculate the entropy, the entropy change of any substance. So let's start first of all, this is how to calculate delta S. Let's start actually in case when we have pure substance. What does it mean pure substance, Shabab? Like when we have steam or when we have refrigerant, the only refrigerant we have considered in this course is the refrigerant 134A in this case. But if we have steam or refrigerant undergo actually a change from, let's say, from one initial state 1 to a final state 2. In this case, to calculate delta S, I will just say delta S is S2 minus S1. This is, Shabab, the total entropy change, which is calculated in kilojoule per Kelvin. But the value listed in the table is a specific value. So is a specific entropy. So the total change of entropy will equal to mass multiplied by the specific change of entropy S2 minus S1. And this value we get from the table using two independent and intensive properties. We can go to the table either for steam table or refrigeration table at a given two properties to calculate this entropy. This entropy, specific entropy, is calculated in kilojoule per kilogram Kelvin. But if we have an isentropic process, if we have steam or refrigerant undergo an isentropic process, what does it mean about isentropic process? Isoentropy, so the entropy is what?
Constant.
Constant. So isentropic, if the entropy is constant, so that means we don't have entropy generation. So that means the process is what? Is reversible, and we don't have any kind of losses in this case. So isentropic process means actually that the entropy remains constant, and isentropic process actually means S is equal to constant, or we can say actually delta S is equal to 0, which is S2 minus S1. In this case, entropy is constant, so S2 is the same as S1, or we can say delta S is equal to 0. Isentropic process, in order to have the entropy constant, that means we don't have any kind of losses within the system. So this process is a isentropic process, reversible process, and also we don't have heat transfer in this case. So the process is as well actually is a adiabatic process, or the heat transfer is equal to 0. Because if we have heat transfer, it will not be actually a reversible process. And in this case, for any kind of irreversibility, as we said, any kind of irreversibility within the system, just to convert it to the form actually of entropy generation. So in this case, the entropy will not be remaining constant if we do have any kind of irreversibilities within the system. So isentropic process mean actually this process is reversible. We don't have any kind of losses, so that the entropy cannot be generated, so the entropy can remain the same. But if I want to keep this entropy the same, that means actually you should not have what? Heat transfer. Because if we have heat transfer to the system, in this case, this term will represent actually a kind of entropy change in this case. So to have delta S equal to 0, entropy generation due to the losses should be 0. That means the system is reversible. And to this term to be 0, the system should be what? Should be adiabatic in this case. So the isentropic process, Shabab, is a reversible adiabatic process in which actually the entropy remains constant, or we can say actually the change of entropy is equal to 0 in this case. But what are the applications for isentropic process? Like expansion and compression process, like in case of turbine. Usually turbines, the Shabab, or compressor, we assume that those processes are actually adiabatic. We don't have heat transfer, and this is close to the real situation. We assume adiabatic expansion in the turbine, or also adiabatic compression in the compressor. This is something close to the reality, the real case. But when we assume actually it is reversible, we cannot have actually a compressor or any device actually to be irreversible. But in some cases, we assume the compression or expansion process inside compressor, turbine, nozzle, diffuser, all of these devices. We may assume the process as isentropic. Then in this case, we don't have any kind of losses. Then we can calculate the maximum work. Then we can compare it to the actual work of this system. Then it gives us indication about what we call actually the isentropic efficiency, which is the ratio between the actual work developed by this turbine divided by the isentropic work in this case. Okay, so inshallah we'll be talking about this course also, how to calculate the isentropic efficiency for compressor and also for turbine. But in some cases, as I told you, we assume the expansion of the compression process as isentropic. So in this case, we can calculate the work out of the turbine to be the maximum work in this case. Then we can compare it to the actual work to calculate what we call the isentropic efficiency. If you look at this process, as you can see, we can represent it on the TS diagram as the process is isentropic. That means the entropy is equal to constant, or delta S in this case is equal to 0. Either the process is expansion from 1 to 2, or the process actually is compression from 2 to 1 in this case. And this is the representation on the TS diagram. As we said, isentropic process is just applied actually for some devices to calculate the maximum work, like the turbine, compressor, and also the case when we have nozzle and when we have diffuser. And actually nozzle and diffuser are part of the turbine and the compressor. The design of the turbine is mainly actually containing actually nozzle as a fixed blade, and for the compressor it contains actually the fixed blade takes the shape of diffuser in order actually to build the pressure within the system, which is the main function of the compressor, to raise the pressure of the system. In case of turbine, we have nozzle to have a velocity jet to raise the velocity of the flow. Then it can drive actually the shaft of the turbine. Okay, so isentropic process can be applied for some cases of expansion and the compression process to calculate the maximum work of the system. Type here is an example. Look here at this example. We have a steam. He said we have a steam in an adiabatic turbine. So the working fluid. Let's look at this example. So it will be the same problem like what we have done in chapter 4 and chapter 5, either closed system problem or open system problem. And we should have to calculate something from chapter 7 here. So let's say here we have a steam turbine. So the device actually is turbine. So we can apply the first law of thermodynamics as we learned in chapter 5. And this is actually a adiabatic turbine. That means the heat transfer is equal to 0. And he gives the inlet condition. The inlet pressure B1 of this turbine is equal to 50 megapascal and 5 megapascal, and the temperature is 450 degrees C, and T1 is equal to 450 degrees C in this case. He said the outlet condition of this turbine, the pressure B2 is equal to 1.4 megapascal in this case. Okay, so we have a steam turbine, adiabatic steam turbine. The inlet condition of a steam, so the working fluid is what? As we said, we have to define the working fluid first. So the working fluid is a steam in this case. Okay, we need to determine the work output of the turbine per unit mass. So we need to calculate the specific work out of this turbine, the value of the specific work, if the process is reversible. So in this case, he said actually the process inside, the expansion process inside this turbine is a reversible process. So what does this mean, Ishida? He said adiabatic turbine, and now he said calculate the work if the process of expansion inside the turbine is a reversible process. What does it mean, adiabatic? Reversible adiabatic means what?
Change in entropy is 0.
Yeah, that means the process is isentropic. That means actually the entropy S2 is the same as S1, because at the exit section he just gives you the pressure. I need two properties in order to apply the first law of thermodynamics and calculate the work. He gave me only one property, which is the pressure. But he said this turbine is adiabatic, and he said calculate the work if the process is reversible. So reversible adiabatic means the process is isentropic, so S2 is the same as S1. But let's apply the first law of thermodynamics as we have learned. So we said Q dot minus work dot equal to M dot multiplied by delta H plus the change in kinetic energy plus the change in the potential energy. So in this case here we have the change in kinetic energy. We don't have any given here, so just will be neglected. And he said we have a adiabatic turbine, so this term is equal to 0. So work dot rate of work will equal to M dot multiplied by delta H. But he didn't give the mass. So in this case, and we need to calculate the specific work in kilojoule per kilogram. So we can divide, actually use the specific form, divide the whole equation by M dot. So the specific work minus the specific work will equal to delta H, which is H2 minus H1. Or we can say the work will equal to H1, the difference in enthalpy H1 minus H2. And this is the specific work should be calculated in kilojoule per kilogram. Is that clear, Shabab?
Yes.
So when he said reversible adiabatic, that means the process is isentropic. You have to understand this. Then we can say the entropy S2 is the same as S1. But how we can calculate H1 and H2? So in this case, given pressure B1 at the inlet of this steam turbine, usually the inlet of the steam turbine here is superheated steam. So it cannot be any other case, but you have to check anyway. So you have in this case actually you have the pressure and you have the temperature. With this pressure, go to table as we have learned, table A5, get the saturation temperature, then compare the saturation temperature with the given temperature. You will find this temperature, given temperature, is greater than the saturation temperature, so the state is superheated. So just I will be going to table A6 with this pressure table, 5 megapascal, and at this temperature we can calculate the value of the enthalpy H1. Okay. Usually at the outlet of a steam turbine, so pressure is given, and we have S2 is the same as S1. So also from point 1 at point 1, I get the enthalpy H1. I have to get also to get the entropy S1 in kilojoule per kilogram K. Okay. So now I have the enthalpy and I have the entropy S1 at point 1. So in this case, so I got S1. Now at point number 2, I have pressure equal to 1.4 megapascal, and S2 is the same as S1. I have pressure with one specific property. So what should we do? I'm just trying to revise with you what you have done actually in chapter 3. Okay. So with this pressure, I will be going again to table A5. I will get S fluid, and I will get the value of S gas, and compare it with the given entropy, which I got actually at point 1. So in this case, you will find the entropy S2, most probably at the exit of the turbine, the state will be saturated mixture. So you will find that S2 is greater than S fluid and less than actually S gas. So the state is saturated mixture, and in this case, we have to calculate the value of X, quality X2. So X2 will equal to S2, which is the same as S1, minus S fluid divided by S gas minus S fluid. You will find in the table also S gas minus S fluid is SFG. You can get the value directly from the table. Then you can calculate X2. But I don't need X2. I need the enthalpy H2. So in this case, at this pressure as well, from table A5, I got S fluid, S gas. I can get also H fluid and H gas in this case. And I have calculated X2. Then we can calculate H2 will equal to H fluid plus X2 multiplied by HFG. You can get here, if you have, instead of H gas, you can get HFG directly. Then we can say H2 will equal to H fluid plus X2 multiplied by HFG in this case. So Shabab, for any problem you have to look, I'm repeating again, you have to look at the working fluid. So here he said steam, then I have to stick to the steam table. Don't go and just apply BV equal to RT and try to search R and T, and then you will invent actually many things in your exam. So you don't need to do this. Working fluid steam, I have to use the steam tables in this case. The idea here of this problem, he said, reversible and adiabatic turbine, that means it is isentropic, so the entropy is constant. Is that clear, Shabab? Is it clear?
Yes.
Type. Okay, type. Let's proceed. Type. This is, Shabab, how we can calculate delta S. If the working fluid is steam or refrigerant, in this case the value is already tabulated in the table based on the experiment. So just I will say delta S is S2 minus S1. For isentropic process, delta S is 0, reversible adiabatic, or S2 is S1, and this is a kind of example. Okay. Type. For any other, if we have the working fluid is incompressible substance, or in case when we have ideal gas, fluid is gas, how we can calculate delta S in this case. So inshallah we'll see today, we'll develop today what is called actually the TDS relation, based on which you will develop an equation based on which we can calculate actually delta S for any working fluid. In case of pure substance like steam or refrigerant, the value is calculated experimentally, so we don't need actually to have a relation in this case. Yes, sir. But if we have any device undergo expansion, let's say from process 1 to 2, we learned how to represent this process on the PV diagram, TV diagram, and on the different diagram actually. But there is one very important diagram which is called actually the Molière diagram. Molière diagram, which is the HS diagram. H, which is enthalpy in kilojoule per Kelvin, and the entropy is a specific entropy kilojoule per kilogram in a specific or total value. HS diagram in general gives us actually, it is called as the Molière diagram. So if we have expansion process, like expansion in a turbine or something, we can represent this process of expansion from point 1 to point 2, from high enthalpy or high pressure and high temperature to low enthalpy and low pressure and low temperature. So in this case, Shabab, this difference delta H from 1 to 2, this difference delta H give us indication about what?
Change in pressure.
About what?
Pressure and temperature.
But yes, difference itself from the inlet to the exit, difference in enthalpy give us indication about what? We just solved this example here. See here?
Change in internal energy.
Delta H gave us indication about what? About the workout based on the first law of thermodynamics. So if you look at the Molière diagram, as this difference increase actually, that means actually delta H, if it is high, that means actually the workout of the system should be high in this case. So delta H in the Molière diagram give us indication about the workout of this system. But what about delta S? Delta S here gives us indication about what?
Change in
About what?
heat.
Yeah, about the heat, but in other words, actually, we said delta S gave us indication about the irreversibilities or the losses within the system, because we said delta S is equal to integration of delta Q over T plus the entropy generation. So usually, this delta S give us indication about the heat transfer, which should contain also some losses, which is a kind of losses, and plus actually the entropy generation, any kind of irreversibilities within the system. just the molecules actually take this energy and dissipate it in the form actually of the kinetic motion of the molecule. So any irreversibilities appears actually in terms of entropy generation. And delta S is equal to delta Q over T plus entropy generation. So that term actually gives us indication about what? About the irreversibilities within the system. So delta S gives us indication about the losses within the system. And that's why, Shabab, if we have isentropic process, isentropic means what, Shabab? The process is just vertical. Delta S is equal to 0. Isentropic process means the process is reversible. In this case, delta S is 0. That means actually we don't have any kind of losses within the system. So the losses are 0 if the process is isentropic. But usually for any actual process, we should have some losses. And in this case, some entropy should be generated. And as I told you last time, this term is always a positive value because you cannot have any process with entropy generation negative value. Even if you are doing a process to reduce the entropy, this is actually also will result in entropy increase. So even in a trial to try to reduce delta S, it will result actually in increase of delta S. And this is the real situation. You cannot do something and reverse it. If you did something, so you did something. So you should have some losses. Okay? Is that clear, Shabab? So delta S gives indication about the irreversibilities. Delta H in the Mollier diagram gives us indication about actually the workout of this system. Also the process, we can represent this process on the temperature entropy diagram. It will be very similar, but the curve will be a little bit less sharp reduction, or the inclination of the curve is just reduced from 1 to 2 as compared to the HS diagram. But if we look here, Shabab, under this curve, the area under the curve, if I took an element, small element, rectangular element, its width here is delta S, and the height is T. So delta area of this element is equal to what? The area of this element is T multiplied by delta S. The length by the width. Okay? But if I integrate it, then I can calculate the total area. So the total area under this curve will equal to what? Integration of TdS. By definition, we defined the entropy last time based on the Clausius inequality, which at the end actually we derive the equality case. The equality case, when we have a reversible process, that the entropy is defined as delta Q over T for the reversible process. So that means in this case, delta Q will equal to what? Based on the definition of the entropy, will equal to T multiplied by TdS. Okay? Or if we integrate to calculate the total heat transfer. So total heat transfer is equal to what? Integration of TdS. That means the area under the curve, Shabab, on the TS diagram for any process gives us indication about what? About the heat transfer. About the heat transfer, exactly. Like what we have done for the work. We have represented the work on the PV diagram, let's say from state 1 up to state 2. And we said the area under the curve on the PV diagram gives us indication about what? About the work, because we said the work for closed system is equal to integration of BdV. But Shabab, the work for open system, inshallah, we'll see in this chapter that the work for open system is equal to integration of VdV, not BdV. Okay? But for closed system, the work is equal to integration of BdV, which is the area under the curve on the PV diagram. So the area under the curve on the PV diagram gives us indication about the work. The area under the curve, the TS diagram, gives us indication about the heat transfer, as the heat transfer is equal to integration of TdS based on the definition of the entropy, based on the Clausius inequality. Okay? Right, how we can, Shabab, if we have any substance other than the pure substance, how we can calculate delta S? For refrigerant or steam, as we said, we can directly use the tables because the values are listed there. So we don't need to develop a relation for those actually fluids or for those substances. Right. What if we have incompressible substance or gas or any other substance? How we can calculate delta S? In this case, we have to develop what's called actually the TDS relations. The TDS relation, based on actually, they have been developed actually based on the first law of thermodynamics. So let's consider a closed system. Undergo actually a reversible process. So the closed system, let's say undergo a closed process, a reversible process, let's say from state 1 up to state 2. So for a closed system, we have delta Q minus delta work is equal to what? Delta U, is it?
Yes.
So we set Q minus work for a closed system is equal to delta U. We are considering here closed system undergo a reversible process. So delta Q minus delta work will equal to delta U. But we have defined the entropy delta U delta S is equal to delta Q over T for actually a reversible process. The process here is reversible. So that means delta Q will equal to what, Shabab? Delta Q is equal to TDS. But for a closed system, we have delta work is equal to what? Is equal to BdV. So we can just take those two relations and substitute here. So in this case, we can say TDS minus BdV, that should equal to delta U. Or we can say TDS, we can take this to the other side, will equal to delta U plus pressure multiplied by delta V, the change of specific volume. And this relation, we call it actually as the first TDS relation. TDS to calculate the entropy. TDS is equal to delta U plus BdV, okay? By definition, we have the enthalpy of the fluid is equal to the internal energy plus the flow energy, which is pressure multiplied by specific volume. So we can say delta H will equal to what, will equal to delta U plus what? We have two parameters, two variables here. So it will be BdV, the differentiation will be BdV plus BdV in this case. All right, delta U plus BdV, this term. Is it the same term here? Is it?
Yes.
It's the same term. So this term is equal to what? Is equal to TDS. So we can just replace this term by TDS. And in this case, we can develop the second TDS relation to calculate the entropy. TDS here will equal to delta H minus BdV. We can take it to the other side. And this is the second TDS relation used actually to calculate the change of entropy for any process. It can be generalized for any process. Okay. But in this case, we can just write down the two TDS relation. How to calculate the change of entropy. Those are differential form. Then in this case, to calculate delta S, we have to do the integration in this case. Okay. So the two TDS relation that we have developed, the first equation, ds will equal to delta U over T plus BdV over temperature, and this is the first relation to calculate delta S. The second relation as function of the enthalpy is equal to delta H over T plus TDS. I just took the temperature and divide actually in both sides. It will equal to delta H over T minus BdV divided by the temperature in this case. This is the first TDS relation, and this is the second TDS relation. Delta S here is function of enthalpy. Delta S here is function of the internal energy. Right, let's take those two relations and see how we can apply for the different cases. So let's consider special cases. I will start first of all with the most easy case, the easiest case, in case when we have incompressible substance. Incompressible, which is what? In case when we have solid or we have actually a liquid substance. Incompressible means what? The density is not affected by pressure, okay? Because it is incompressible, either solid or liquid. So the density, as we have said before, the density is constant in this case. And density by definition is 1 over a specific volume. So that means the specific volume in this case remains constant in case when we have in case when we have incompressible substance in this case. Okay. طيب if volume here is constant, so delta V will equal to what? Delta V will equal to
0.
will equal to 0 in this case. And based on this, we can calculate delta S for incompressible substance will equal to delta U over T. But do you recall actually from chapter 4 how we can calculate delta U? If you remember, we said delta U for incompressible substance will equal to what? C average multiplied by delta T. And this C average is calculated from where? From table A3. For incompressible substance, we calculate the average temperature. In this case, we calculate T average for a process which is T1 plus T2 divided by 2. Take this average temperature, go to table A3, then we can calculate C average. And we say that in case of incompressible substance, either if we have solid or liquid, in this case we don't have a specific heat at constant temperature or a specific heat at constant volume. In this case, we call it actually in general as C. We call it C average because if we have temperature difference, then in this case we have to calculate the average temperature, go to table A3, then we can calculate C average. So delta U is equal to C average multiplied by delta T. So just substitute here, which is C average delta T divided by T. But what I need actually is the total entropy. I don't need the differentiation. Then in this case we have to integrate from T1 up to T2, and this delta S from 1 to S2. The integration will be actually S2 minus S1 or delta S. Then we can say delta S will equal to integration of C average dt. C average has constant value. We consider it average value, so we can just take this term outside it. So it will be integration of delta T over T. What is the integration of delta T over T? Should equal to ln T, exactly. So ln T2 divided by ln T1 in this case. Ln T2 minus ln T1. So that should equal to C average multiplied by ln T2 over T1, which is the same as ln T2 minus ln T1. Okay, Shabab? So this delta S calculated in kilojoule per kilogram Kelvin. This is also CV is in kilojoule per kilogram Kelvin. This from table A3, depending on the working fluid, incompressible substance. Then we can calculate delta S will equal to C average ln T2 over T1. And again, Shabab, I have to remind here that this temperature T2 and T1 should be in Kelvin in this case. Is that clear, Shabab?
Clear.
So in case of any other substance other than steam or refrigerant, I will just say delta S is S2 minus S1. S2 and S1, I can just go to the table at state 1 and state 2. Then I can calculate delta S in this case. Okay. But any other substance, we have to develop the TDS relation in order to calculate the change of entropy delta S in this case. We have two relations. One is function of the internal energy and one is function of the enthalpy in this case. We are considering here special cases. Today, inshallah, we'll be just considering this case in case of incompressible substance like solid or liquid, how we can calculate the change of entropy if we have any incompressible substance undergo a process or a change actually from state 1 to state 2, how to calculate delta S in this case. Inshallah, next time we will learn how to calculate delta S in case when the working fluid is gas. But you know, in case of gases, we have actually delta H, delta U. We have two approaches. We have the constant specific heat analysis and the variable specific heat analysis. So inshallah, to calculate delta S for gases, inshallah next time I will learn how to calculate delta S following the constant specific heat analysis. Delta U will equal to CV dt, delta H will equal to CV dt. Okay, we can consider CV and CV as constant, and then we can consider the constant specific heat analysis. Variable specific heat analysis, inshallah, we will just reformulate this formula and we will come up actually with another formula to get it as function actually of the entropy, and the entropy will be calculated from table A17 to A25 again. So yeah, Yeah, let's forget about this right now. In case of ideal gas, inshallah, next time we'll learn how to calculate delta S. Okay. And also we'll consider the special case when we have isentropic process, delta S is equal to 0. And based on this, inshallah, we'll develop the isentropic relation. How we can relate the pressure with temperature, with the volume, all of these properties, how they are related if the process is isentropic. Okay. And also this will be done based on constant specific heat and variable specific heat as well. Okay. But you will find in this chapter, we are writing too many equations, but those equations can be developed there. You don't need to keep something in mind, but you have to keep your understanding so that you can develop the equation. So just for the TDS relation, as we have seen, for the case of incompressible substance, we just used the relation incompressible volume is constant. So we said delta V is equal to 0. This term is 0. So delta S will equal to delta U over T. And we did the integration. Then we can get delta S, which is C average multiplied by ln T2 over T1. But if we have a incompressible substance undergo an isentropic process, delta S is equal to 0. When we have delta S is equal to 0 based on this equation, delta S is equal to 0 when? Look at this equation.
When temperature equal.
Exactly. So if we have yes, so if we have incompressible substance undergo an isentropic process, reversible process, that means this process is as well what? Isothermal. So the temperature should also be constant. So it is reversible, adiabatic, isentropic, and also it is isothermal if the substance actually is incompressible substance. Okay. طيب here شباب is an example, يعني it's a kind of simple one. Look at this example. About the time. Still we have time. طيب here we have liquid methane يا شباب. Liquid methane is يعني used in different cryogenic application in the liquid form يعني. So usually يا شباب methane, if it is in the gaseous form, we need actually to compress it in the cylinder. So in this case, to have a significant amount of this methane, we have to compress it actually to a high pressure in a cylinder. But usually if I need more flow rate, that means in this case I have to liquefy this methane. So it will be converted to liquid in this case. Okay. Like actually all of the gas producing wells, actually they should have a kind of liquefaction plant in order actually to liquefy these gases, so that we can put them actually inside container, inside ships or something, then we can export them. But actually in the gaseous form, we cannot provide actually the space for the gas, or actually if in this case we don't have significant amount of this gas, then in this case we have to compress it actually to very high pressure. And this is something is expensive first of all, and it is dangerous as well to have a gas, explosive gas under high pressure. So usually in different cryogenic application in the liquid form, usually we liquefy the gas. So methane, it's not methane, we can say natural gas. Yes, sir. So in different application, usually natural gas, most of it, more than 90% is methane. So we call natural gas as methane, which we get actually from petroleum wells or something we can get in addition to petroleum, liquid petroleum or crude oil. We can get also some gases in this case. Usually we have some natural gas type. Anyway, the methane critical temperature or natural gas critical temperature is 191 Kelvin. That means it is minus 82 degrees C. You can imagine this is the critical temperature above which actually we cannot distinguish between the liquid phase and the vapor phase. That means to have methane in the liquid form, it should be actually below this critical temperature. Okay. So to have methane in the liquid form, it has to be actually at minus 82 degrees C in this case. And it is, which is equivalent to 191 Kelvin in this case. The properties of liquid methane at various pressure and temperature are listed in this table. So this table is just given for you as indicative example here. So in your exam, I will not provide you this table, but just this to give you يعني idea about the actual value of the enthalpy, the actual properties of methane at different temperature and pressure. Here you have density, you have the enthalpy, you have entropy, and also you have the specific heat in this case. Okay. But يعني if it is in your exam, if we have liquid or solid substance, that means the substance is incompressible. So in this case, to calculate delta S, I will be using this relation. But here, yani, this is a very important fluid, which is liquid methane. So they should have some table for this value. Type those properties are listed here at different temperature. At temperature 110 Kelvin, we have for a range of pressure, we can get the properties. Also at temperature 120, and for a range of pressure, we can get also the properties. He said we have methane pump, a pump actually that is used to compress the methane from inlet pressure 1 megapascal. Inlet temperature 110 Kelvin is compressed to pressure, high pressure equal to 5 megapascal, and temperature T2 is equal to 120 Kelvin in this case. And he said we need actually to determine the entropy change of this liquid methane undergo this compression process. First of all, using the value in the table. Value in the table, شباب, this is based on experiment, real life measurement. So that should be the actual value of compressed methane. And then we can compare it actually based on the approximations, the TDS relations that we have approximated actually that C as average value we can get from table A3. This is a kind of approximation. That's why this is not typically equal. So this is a kind of approximation. So we need to calculate it using this approximated relation and compare it with the actual values listed in this table. Type here, شباب, in this table. If I need to calculate the entropy from the table, he gives me the temperature at the inlet 110. So this is 110. And the pressure 1 megapascal at 1 megapascal. Here is the entropy, in this case, will equal to 4.875 kilojoule per kilogram Kelvin. Type at T2 120. So, and the pressure is 5 megapascal. So the entropy in this case will equal to 5.145 in this case. So the difference in entropy delta S will be just the difference between the two values in this case. Type the second case, this is the actual difference in entropy. Type the second case using this approximation, C average ln T2 over T1. You have two options to calculate C average. Here in this table, he gives you the specific heat, CB1, at temperature T1 and this pressure 1 megapascal. And we have CB2 at temperature 120 and the pressure 5 megapascal. This is the value. Then to get the average specific heat, we can just say CB1 plus CB2 divided by 2, and then we can get this value. The other option is what, Shabab? Because in this problem, this very special case problem, we have a table that will not be available anymore. Yeah. So the other option is to calculate the average temperature. We have T1 and T2. T1 is 110, T2 is 120. Calculate the average value, go to table A3 for methane. Then in this case, you will get the average specific heat, in this case for liquid methane. Okay, it should be this value also as well. Type, let's apply the approximation delta S will equal to C average ln T2 over T1. This is C average and this is T2 and T1. Then we can calculate delta S. Type to calculate the error. Delta S error should be what, Shabab? Actual minus ideal divided by actual. Which one is the actual? The value from where?
From the table.
The value from the table that we have calculated, which is delta S. So delta S actual, this value 0.27 minus delta S ideal, which is 0.3, divided by what, Shabab? Divided by the actual value. So when you calculate the error, this error should be calculated with respect to actually in reference to the actual value, not the ideal value. So divided by delta S actual. This error will be a kind of 12%. Okay. طيب I will stop here today.